rules of quantum field theory, no problem. Absolutely no problem. And that calculation will lead you to this formula. This you can check. This is done in Hazel Martin's book, where this GE and GM, these are nothing but combinations of A1 and A2, which I have written over there. Is it clear? That I could not calculate this because I don't know the proton current. Okay. So I parameterize the proton current, plug it into the formula for scattering cross section, and then I can calculate using the rules of quantum field theory. Alright, but the calculation will involve these two unknown functions, and a linear combination of these two unknown functions are this GE and GM. So this is not a God-given formula, this can be calculated. The only trouble is the calculation will involve unknown form factors. Alright, so this is the trouble when we have a composite particle.
That is Q mu.
Which one?
Second part, A1 and A2 are unknown functions.
So Lorentz inverse contracts on Q mu, sigma mu.
No, wait a minute. I think I made a mistake here. J mu is yes, so gamma mu is okay. I think I should have contracted mu. Sorry, I should have contracted mu. I was a bit cavalier there. This is the right way of writing. Sorry. But this kind of thing immediately gives us a very important idea, that is, why don't I write this as an unknown current? The only thing is I cannot write down it as U bar U, because although I have a single proton in the final state and I know its Dirac wave function, I don't know what the hell is here, because this can be anything. But the essential idea is I parameterize by my ignorance about the process by introducing unknown functions which are like form factors. Of course, they are not the same as the form factors for electron-proton scattering, but let me introduce unknown form factors. What happens? So I will write the amplitude for this process as L mu. This stands for electronic current, which is known from quantum field theory, and this as H, and this fellow is the hadronic current, which I do not know. So, now, amplitude is not the probability. This we know from quantum mechanics. Mod square of the amplitude is the probability. So, in the cross section, what I will go is, let me put a name here, let me give it a name here. So, let me call it some amplitude, let us say F. And then what will be F mod square? This will have many factors, okay? That's why I write this symbol here. That I am only putting those terms which are important on my understanding. And this will be obvious, this will be L mu G H mu, and then L mu dagger, mod square means L mu dagger, and then H nu dagger. And let me write this as L mu, L mu, L nu, and then H mu dagger, and I give a name, I call it L mu mu. In textbook, this is normally referred to as the electronic tensor. And this is known, of course, and this is the electronic this, of course, is but now you know how to handle unknown things.
Then not new, I think.
Sorry?
L,
L mu, H nu. So,
L mu written two times.
oh. Sorry. So what I do? Now you know what I do. I introduce unknown functions because I do not know from any fundamental physics what to write for H nu. So I do that. But before that, let me do a counting, that is what are the independent variables. Now remember, in the case of electron-proton scattering, it was a q square here, because there q square is the only unknown quantity. Now those of you who understand elementary scattering processes will immediately realize that electron-proton scattering, however complicated it may be, it was basically a 2 going to 2 scattering. Right? And 2 going to 2 scattering is basically basically dependent on the scattering angle. That's all. And that scattering angle is represented by q square, the momentum transfer. The momentum transfer is dependent on the scattering angle. So there was only one independent variable, q square. But here that does not there because the constraints are different. Here I have an unknown final state f, whose energy momentum I don't know. So in this process there will be two unknowns. One is of course q square, which is actually written by and this of course is k prime minus k whole square. So this is the for momentum transfer. And if you break it up and neglect the electron mass, K square is the electron mass, K prime square is the electron mass, neglect them, because in this high energy processes, and this will simply be 2
Why it is minus 2 K over K?
Okay. Sorry. I wrote minus here. Sorry. So clearly this is a positive quantity. So Q square is a negative quantity. That means the momentum transfer is a space-like vector. This Q square is positive. And the other important variable is, so I remind you that Q square is a positive quantity and Q square is a small q square is a negative quantity. And the second one is of course mu, which is the energy lost by the electron. So this is obviously positive. Now this was not independent because you had a proton in the final state. So if you go back, you will find that E prime, they are not independent variables, they are fixed by the energy momentum transfer in the relation. But those of you who are interested in Lorentz invariant quantities, because they are always giving you confidence that whatever I am getting is not dependent on the frame. Make yourself convinced that this is basically P dot Q over M, where P is the force momentum of the proton. Now this is easy because the force momentum of the proton, where I wrote it. So P is actually in the lab frame is mass of the proton. Now since this is a Lorentz invariant quantity, you can calculate it in any frame, and if you calculate it in the lab frame, you will find that this reduces to the energy lost by the electron, E minus V prime. So it's all very nice. So I have two independent variables. Now I write down the how do I arrive at this form? There are a lot of symmetry argument that went into it. That is, our main task is to construct a second rank tensor from the available quantities, which is the four momentum of the proton and the momentum transfer in the electron. And there can be unknown functions which are functions of q square and p. These are Lorentz invariant quantities. Now those of you who, maybe I do one thing, I think at this point I can say that the next few things will be understood only by the people who know a little bit of quantum field theory and gauge invariance. So the others can switch off or go out 40. But those of you who know a little bit of quantum field theory and symmetry arguments can stay here and see.
Alright, the P is outside, so you can have P and then come back if you want.
No, I mean, see, I don't want to waste time for this because everybody, MSc students may not understand it at all. And therefore there is no point in confining it. Many of the PhD students may be knowing it. So there is no point in confining them for this discussion. The point is, see, what I was writing as current always satisfies a property. That is, the current is comes out. That is, P mu J mu should be equal to 0. Now, the currents that I have been writing here are currents in the momentum space. That's why I write Q bar, etc. So, in momentum space,